So where we're going to begin now is to sort of pick apart some of these concepts. And where we're going to start is with this idea of force in the rotational sense, which is called torque. So torque isn't exactly just a force. It's a little bit more complicated than that. So I'm going to go into some basic torque calculations and concepts in this video. Right? So torque is written with the Greek letter tau, it just looks like a little cursive T, right? And it really has to do with a force, but it also is relative to the distance away from the center of mass. So remember, here's the center of mass, some distance away from that point, or some distance away from the point of rotation, so some fixed position where it's going to rotate. Now, recognize that when I fix this, this becomes the point of rotation over here, and so when I push on this object, the distance is from where the force is exerted to here. If there is no fixed position, then I exert a force here, and the distance is going to be to the center of mass. Well, the center of mass is still the point of rotation. It's where it's rotating about, right? So torque really is a force, and it is a force perpendicular to the distance, and this is the distance away from a point of rotation. So distance away from a point of rotation, either fixed or the center of mass. And then this is just like whatever your applied force is, but remember that it is going to be only the force that is perpendicular to the, to the object, right? So if I push at an angle like this, right, it would only be the force that makes a 90-degree angle with it. Right? And that's all we're going to look at for now. And actually, I'm going to even simplify it, and we're going to say that we're not even going to deal with any problems to start with that are around the center of mass, because we're just going to make every object be massless. Right? So what does that really mean? If I were to take, say, a door, right, and we're just going to assume that the door has no mass, or like a negligible mass, right, and I were to fix the end of it right here, right, if I were to apply a force, right, so here's where the hinge is, if I were to apply a force at the end of the door, and just for simplicity's sake, let's say that the door is 1 meter in length. So let's say that I push on this door at a 90-degree angle, so perfectly perpendicular, at 10 newtons. Well, if I wanted to calculate the torque, it would be, 10, and the unit is newtons times meters. Now, this isn't work, right? Because remember that work is going to be parallel to the motion, right? Where this is perpendicular to the motion. So the unit for torque is newton meters, but it is not the same as joules or newtons times meters. That is work. All right, so let's say then I wanted to apply the same amount of torque, but instead of pushing the door on the very end, let's say that I applied the force here, right in the center of the door. Right? So the distance now from the point of rotation would be just a half of a meter. So to get the same 10 newton meters of torque, I would have to apply a force of 20 newtons right here, so that the torque would be 0.5 times 20 would be 10 newton meters. So to get this door to accelerate in the angular direction by applying a net torque to it, if I wanted to have the same acceleration and I was pushing out here, it would only take me 10 newtons, whereas if I was pushing here, it would take 20 newtons, right? So the force is going to change relative to the distance to create the same angular acceleration. All right, so these are just very basic, like torque, force times distance, right? And remember Newton's second law, or Newton's laws say that a net force, right, so remember F net, is going to cause some acceleration. Right, in the last video, I had, this equation, torque is going to cause, this mass sort of idea times acceleration. But we don't really want to deal with that to start with. We want to actually look at the whole idea of equilibrium, right? So remember, equilibrium in terms of Newton's laws is when there's no net force. And in this case, we're going to say there's no net torques. So if there's no net torque, describe the motion of that object. Really, there's two instances. One, the object's not moving. And in the other problems, we're always saying, oh, the object is at rest. Well, remember, that's a translational term. Really, there's no rotation. That's kind of how we would say that in a rotational problem. Or we could then look at it being sort of a dynamic equilibrium situation where you had some rotation, but rotation at a constant velocity, right? And even to simplify it more, we're not even going to be dealing with this right now. We're only just going to look at problems of equilibrium where there's no rotation, right? So let me give you an example of a problem and an equilibrium expression in terms of torques. So let's say you had a seesaw, right? And you have a board of negligible mass, right? So we're going to say we don't have to worry at all about the mass of this thing, right? We're just going to say it doesn't even matter. And over here on the end of the board, you have one, like the little brother, whatever, and he's standing on the end of the board. Okay? And let's say that little brother on the end of the board weighs 20 kilograms. Then, over on this side of the board, you want to put Big Brother, and Big Brother wants to balance this out, right? So when we're in equilibrium and we're trying to balance something out, we're trying to make it have zero net torque, meaning that everything that's causing it to want to go to the right, like this, must be equal to everything that's causing it to want to go left so that no spinning occurs. Right? So it really is torques. So let's say like the whole board, we got to give the board a length. Let's just say it's 4 meters. Right? So that means there's 2 meters over here, and there's 2 meters of space over here. So if this 20 kilogram kid is over here exerting a force downwards, his torque that's going to make it go to the right must be equal to the torques to the left. Or the torques that, when we say right, we're really talking about clockwise torques. And things that are going to the left, these are going to be counterclockwise torques, right? And they have to be equal. So the torque over here, we know, is going to be the force of this kid that he's exerting some distance away, which would be 2 meters, right? So if we want to just write that down, 20 times 10, right, which would be the kid's weight, times the distance, which would be 2. All right, so let's say brother is over here, and brother wants to figure out where he needs to stand, and let's say big brother weighs 35 kilograms, right? So we want to place him somewhere where his counterclockwise push this way is going to equal this direction over here. So counterclockwise over here, we're going to say his force times gravity, or his force, his mass times gravity, so it's going to be 35 times 10 to get the force. And then really the question is, like, where's he got to stand? So what would the distance he would have to position himself away from the point of rotation such that he would create equivalent torque to his brother over on the other side? So if I grab a calculator here, we get 20 times 10 times 2, which is just 400, right? So we got 400 Newton meters of torque over here. And we want to say, okay, well, that's 350 times distance. Well, what is the distance? So 400 divided by 350 says 1.14 meters. So if this brother were to stand right here, 1.14 meters away, then he would create equal torque to his brother over on the other side, and they would balance each other out. All right, so all of our introductory torque problems are all going to be like this, where we have a massless board, right, and or object, some point of rotation, and we're trying to balance it. We're trying to make all of the forces or torques that make it go clockwise balance with all of the torques that make it want to go counterclockwise. Once we move on, we're going to actually add mass to this board and see what happens. And then we'll move further, and then we'll start to talk about when we're not in equilibrium and actually when torque is going to cause some sort of angular acceleration and we get work and change